to start then, we have Andrew Watson. So if you'd like to share your screen, Andrew, you'll have 2 minutes from when you start.
Sure. Okay, that working fine?
Yep, that's fine.
Great. Right, so this is going to be a quick introduction to the main recent fault. This is a right lateral strike slip fault in western Iran in the Zagros. It's seismically active, and it also tracks along the suture of the Arabian and Eurasian plates, the collision of which is sort of driving into seismic motion on this fault. So we're interested in this for two perspectives: one, the sort of seismic hazard perspective, and two, understanding sort of the distribution of deformation in Iran from continental collision. So there's been some previous work to estimate the slip on this fault, and that's come from either GNSS estimates or geological, geomorphological fieldwork estimates. There's been no previously published INSAR work, so that's where we're stepping in. We're using Sentinel-1, looking at these 4 tracks up here, and this is something we want to sort of make velocity maps, and then we're hoping to expand further to a velocity field for the Zagros in Iran. So methodology-wise, using the LIX system and LIX Basio time series, so small baseline. We're doing atmospheric corrections with GACOS. I'm also experimenting with a few other things like trying to remove co- and post-seismic earthquake signals. So this is an attempt for getting rid of the magnitude 7.3 Sarpol Zahab earthquake in 2017, and also calculating the spatial correlation of our data, and that we can then propagate through our decomposition. So we take our ascending and descending tracks, our 2 look directions, and then we decompose those to get fault parallel velocity with hopefully a decent estimate of the errors. So once we have that fault parallel velocity, we're using a 2D screw dislocation model essentially, and a Bayesian approach, the same one that Iqbal Hussain used for some of his papers, to try and estimate the slip rate on this fault. So our sort of preliminary results, this is from 2 of those frames, descending and ascending. Merge those together, we've estimated a slip rate of 3.8 plus or minus about 2 mil a year. We can't get the locking depth, it's very poorly constrained. We can set a lower bound of somewhere like 18 kilometers, which is what we fixed it to for this model. And this is consistent with the GNSS, which is good, but it isn't consistent with some of those longer term geological estimates, which is something we're looking into more. Thank you.
Brilliant. Thanks so much, Andrew. Okay, so we've now got a couple of minutes for any quick questions via Zoom. Well, I'll ask one while waiting. What's the next steps then, Andrew?
So I want to get, there's the rest of those, there's 2 more frames, and those 4 frames also have a 4-frame overlap area. So once all the time series cleared up, the earthquakes are dealt with, all of that, I want to look at that merged area, and hopefully that'll really squish the noise down. And then from there, we can expand to the rest of the Zagros, hopefully with this methodology, and look at more faults and picking out other features like groundwater and basin dynamics and things like that.
Okay, great. And there's a quick question there then from Alex Copley. Does it look like it's creeping?
I don't think so. I think there's quite a lot of noise, especially around the fault, and there's annoyingly, because of where the fault runs, there's then basins next to that fault, and quite a few of those have agriculture and subsidence. So you end up with big areas where you can't hugely trust what you're seeing because it's probably groundwater. But at some point, I took the creep thing out of the inversion. At some point, I will try adding it back in and see what it spits out. For curiosity.
Great. Thanks so much, Andrew. So remember, if you put any future questions for Andrew now into the Slack for a post session. Great. If we move on now to Roberta Wilkinson. You just want to share your screen, Roberta? Great. Thank you.
See that?
Yeah, we can see that. That's great.
Okay, so hi everyone. I'm Roberta. I'm a PhD student at Oxford. I work on Central Asian faults. And in this part of my project, I'm looking at the Zylisky Rangefront Fault in southeastern Kazakhstan. And this lies at the northernmost edge of the Tian Shan. And while there are historical records of big earthquakes in the region, no earthquake's been conclusively tied to this particular rangefront fault. But we do know it's active. The rangefront was recently mapped by colleagues who found strong evidence for Holocene faulting, with scarps for about 250 kilometers along the rangefront and a slip rate of about 1 or 2 millimeters a year. The scarps are discontinuous, probably because they've been buried by loess or eroded or destroyed by humans, and it's just been a long time since the last earthquake. So the fault also runs beneath the city of Almaty, and in a lot of places there's a big canal that's been built on top of it too. And we had no knowledge about individual events on this range front fault, so we wanted to trench it, but good trenching sites are kind of few and far between. But we did identify this one here, this green star, which is about 100 kilometers to the east of Almaty. So we trenched an alluvial fan surface, and the offset layers in the two colluvial wedges that we exposed suggest that there were 2 earthquakes, each with around a meter or so of slip. And we did luminescence dating, which tightly constrains the penultimate earthquake to about 10,000 years. And then the most recent event is less well constrained, and it's probably between about 10 and 2,000 years. Magnitude estimates for the last earthquake are in the high 6s and 7s, but the slip in our trench is much smaller than what we would expect from a nearby slip estimate. So perhaps we kind of trenched a secondary fault strand, which doesn't record all of the slip in these earthquakes, and therefore maybe our slip estimates and magnitudes should be considered minima. But basically our results show that the range front fault is active and potentially very dangerous, and it allows, and also that it follows the pattern of big earthquakes with recurrence intervals of thousands of years, which seem kind of characteristic to this region.
Brilliant. Thank you very much, Roberta. Okay, if there are any questions, again, please type them into Zoom. So one question from Tim to kick off. Could surface fault slip maybe just an underestimate, even if they're on the main fault?
Yeah, for sure. Yeah. Even if it were the main fault, it could still be an underestimate, but I think it's important to get the minimum, a minimum estimate of the sorts of sizes because it's so close to the city as well.
Is there one for me? Is there any evidence that that there is another main strand in the geomorphology, for example? Is there another site that you would like to trench now based on this information, if you could get back there?
Yeah, so there's not a specific, we can't see 2 strands here, but as I said, it's quite degraded all the way through, and they're not continuous, so it's really difficult to kind of piece together the actual length of each segment, or if there is segmentation, etc. But we really do want to go back and trench it more, and that was a plan this summer, but obviously it's been postponed. And I'll be looking at various bits of imagery and Pleiades stems and stuff to try and identify places that we can do that. Fantastic.
Okay, great. Thanks, everyone. So we'll again move on. More questions for Roberta in the Slack, and hopefully we'll have a good discussion there for all the posters. So we'll move on then to Yu Jiang. Yu, if you'd like to share your screen.
It is working well?
Yeah, that's fine. We can see it. And you've got 2 minutes for your pitch.
Hello, everyone. This is Yu from Liverpool. I'm going to present a new fault slip distribution inversion algorithm, which is based on a new crack model. As we all know that fault slip distribution inversions are ill-posed problems, and the regularizations are required to avoid unrealistic slip distribution. Regularizations in the previous research include kinematic models, for example, the Laplacian smoothing and the self-similarity, and also the mechanical model, for example, uniform stress drop in the whole fault plane. In our research, a new lab-derived crack model is introduced to make a regularization, and this new crack model allows constant stress drop at the center while keeping finite stress at the tip, which is more realistic than the previous models. And the workflow is shown in figure 2, which is based on our WGB's method from observed rapid phase to we do phase downsampling and data weighting, and then to construct the likelihood function. And the Bayesian approach is used to estimate the crack model parameters, and finally calculate the model the fault slip. Also, we design a synthetic test for the demonstration. In the synthetic test, the slip is 15 centimeter in the center and 5 centimeter around the center. And the inversion with the slippery and our method show perfect in performance. It revealed the correct location of the crack center and as well the maximum slip. And the RMS of slip residue is 2 centimeters for slippery and 1.5 for our method, which is more or less the same thing. But the thing I want to highlight is that the numbers of parameters are huge, reduced in our new method, which is 200 for slippery and only 6 in our method. And the conclusion is we introduce a new level-based crack model into the slip distribution inversion, and we validated through a single crack. And in the future, a more complicated and realistic slip distribution will be used for validation. Thank you. That's all. I'm looking for any comments or suggestions.
That's great. Thank you very much, you. Any questions here? So one from Jess Hawthorne. How do you decide on the width of the high stress region at the edge? Should the width be the same around all edges?
Based on the, yeah, thank you, Jesse. Yes, yes, I think we decided this. If we consider a more large earthquakes, that the stress drop is more complex. But for small events like our synthetic case or the case we study in the earthquake swarm, we always see that the stress drop is more compact in a small region. So I guess it should be I think it's the limitation of the method, but I think it should be enough for a small event. Yeah.
Thank you. Any more questions? So Tim says, how could the method be extended to large earthquakes with multiple slipping patches? Okay, that's exactly what I was going to ask too, Tim.
Yeah. Yeah. I would say I want to answer the second part. Yes, our method could be used to invert the slip distribution in multiple patches, which is I show in the last COMET student meeting. Yes, we have the ability. Yes, that I want to say. Yeah.
Okay, that's brilliant. Thank you, you. Okay, so we'll move on. Again, please put any more questions for you if you have them burning now into the Slack. Okay, so next up we have Jack McGrath. So, Jack, can you share your screen, please, when you're ready?
Are we good?
Brilliant. Yeah, we can see that, and we've got 2 minutes whenever you're ready to start.
Cracking. So the aim of this project is to try and get a 3D velocity field across central South Island and the Southern Alps, marked with the Alpine Fault here. And one of the reasons we picked this area is because it's very heavily covered by INSAR tracks, as well as quite a dense network of horizontal GPS. So if I was to, so first off, we've taken the LOS velocities for each track. So here, positive is it involves a range increase for each of the 4. 125 is quite messy. I'm not sure entirely why this is, but I think there's a lot of contamination from Kaikoura has fed into it, which is part of the problem we have with there, which has led to some quite large standard deviations on 3 of the tracks, up to about 10 millimeters per year. One exception is this ascending track here, though, which has very good standard deviations on the LOS velocity. That's more of around 1-2 millimeters per year. That's probably due to the vast amount more interferograms that went into this track than the other ones for our selection process. So what we've done is we've gridded these onto a 1 kilometer grid, and we've inverted every pixel that is overlain by at least 3 tracks into a fault parallel and to a vertical velocity. We've tried to constrain the fault perpendicular velocities by using the horizontal GPS fields. And along this black line here is where a GPS vertical velocity transect was carried out in the 90s. So to compare a profile along there with the GPS, so the blue dots are the GPS vertical velocities, black is what we've got from the INSAR. We can see from the first 30 kilometers or so that we get quite a good fit with the obvious corollary of these are fairly significant error bars. And if I was to also compare that to some of our fault parallel velocities, if I was to use a simple screw dislocation model, we can see again for the first 20, 30 kilometers, it works quite well with a 15 to 20 kilometer locking depth. Okay, thank you.
Brilliant. Thank you very much for that. Any questions? I've got one to start then, which is that it looked like in your screw dislocation, it looked like you had centered the screw dislocation on the fault. Is that assuming there's no dip in the Alpine fault?
That's assuming that there's a 50-degree dip on the Alpine fault. Okay. That's what I'd originally done, but then I've just. Oh no! Sorry, that's just a vertical fault. One of the things I've got to do in the future is just include that little bit of an offset to try and line it up properly.
And in the vertical, what did you think that mismatch was as you go further away to the south?
I suspect that's due to the fact that I've not done a great job at removing the long wavelength noise yet. So next step's going to be to use GACOS to do it. Right now I've just used a linear APS filter, but I'm going to redo it using the LIC system because right now I've used my frames don't match up perfectly with the GACOS ones. So hopefully once I've done that, we'll remove that quite well.
So Alex Copley has actually got a related question, which it says, well, how close did you even expect to be able to match the GPS verticals in the 90, and could there be some temporal variability in the real vertical definitions?
I don't know. That's the only really vertical transect that they've done in that time. But if you look at the horizontals in this area, there's not been much variability in the horizontal rates. So if you move further to the north, then you've still got a large effect from Kaikoura. But in this area, the horizontal hasn't changed. So I'm making the assumption for now that there's been very little change in the vertical as well.
Okay, great. Thanks very much. So, for Jack in the Slack channel, please, for his poster. Sorry, Tim was muting everyone and I think has just muted me for a second as well. So we'll move on then to our final poster, which is Chris Rollins. Chris, if you could share, please, whenever you're ready.
Sure. Rich, you may be looking at an earlier version of the program. I think we have 2 more after this, but I don't want to mess you up, so that's fine.
Oh, maybe I am.
Yeah, it's going to be Faye and then Wendy.
Okay, thank you very much.
Yeah, sure. So, all right. So, as Yasser, Milan, Scott, and others have described already, COMET is home of the LIXAR, INSAR processing and workflow, which is taking Sentinel-1 data and making interferograms, time series, and velocities, and publish them and making them freely available for anybody to use on the LIXAR portal. And this shows actually it's a couple months old. Yasser showed some newer maps yesterday, but this is
our. So you know, Chris, we can't see anything. Are you expecting to be sharing here?
Oh, that would help. Okay. Share screen.
Yeah.
Okay.
That's coming through now. Yeah, we can see that. Brilliant. Thanks very much. Right.
So this is this black region here on the left is our area of current coverage, our best current coverage, and this is in Anatolia. So this is the Alpine Himalaya belt, which starts from southern Europe to Southeast Asia. The reason Anatolia is we have such good coverage there is because my predecessor Jonathan and Rich before him and along with him and many other people have done a lot of work grabbing the first 5 years of Sentinel-1 data in Anatolia, processing it, making over 30,000 interferograms covering almost 1 million square kilometers, and making maps of present-day crustal surface velocity. So what Jonathan, Richard, and others have done is they've taken that, merged it with a GPS velocity data set, and converted it to a map of the crustal strain rates at the surface per unit time. So crustal bending year in, year out. And so what I'm looking at is, what does this mean for the likelihoods of earthquakes? So what we do is we take Jonathan and Richard and others' strain map, as you see here on the left. And what we do is we assume that those strain rates hold down to 16 kilometers depth, which is a good value for the locking depth of the North Anatolian faults from work by Ekbal Hussein and others. You can assume something about the rigidity of the crust. We just assume a constant shear modulus. And you can convert this to units of moment, which is basically earthquake size or earthquake potential, if you like. And this is a map, it's just a scalar function. This is a map of moment buildup rate. You just look at the total moment buildup rate in Anatolia. It peaks at a value of 3 times 10 to the 19th Newton meters per year, which is equivalent, for example, to an 8.0 earthquake every 40 years. But we know that earthquakes come in a variety of sizes and shapes. And so what we want to do is use the instrumental seismic catalog to learn how large, moderate, and small earthquakes might team up over the long term to release slack in the system as fast as it accrues due to this crustal bending that we image from Sentinel-1 data. And just to fly ahead to the result, so the axes here are magnitude on the x-axis, and then the rate of earthquakes of or at least each magnitude on the y-axis for a given magnitude. And this is the instrumental catalog that I just showed you. So we have the Erzincan earthquake of 1939, magnitude 7.8 up here. And somewhere in Turkey, once about every year, we have about a 5.7 or greater earthquake. And once about every 10 years in the instrumental catalog, we have a 7.0 or greater earthquake, somewhere in that big box. And then it goes up to the Erzincan earthquake at the top, as well as the Izmit earthquake, which was a 7.6. So we use this as a guide and develop a long-term earthquake likelihoods model. I can describe more about this in person, but it is fit to this and a couple of assumptions about the relative partitioning of earthquake sizes. And the weighted mean long-term earthquake model is this bold dashed line here. So you can see it as similar sort of rates of earthquakes, and you can read out the PDFs of the recurrence interval of earthquakes of each magnitude, as well as of the largest earthquake you might ever expect to see in this big box. So thanks.
Brilliant. Thank you very much, Chris. Okay, so I think we've got time maybe for just one quick question. So Ekbal got in there with fastest finger first. How does the strain concentration on the North Anatolian fault affect the likelihood model?
So yes, the density, the magnitude of strain, the more strain on this, the steeper the velocity gradient across this, the more earthquake potential builds up over time. It may average out spatially to kind of be the same as long as you look at a large enough area, but we're actually looking at that right now. So yeah, it's important to get to resolve the strain field as well as possible, which is why part of why this work of Jonathan, Richard, and others, and Ekbal, and before that is such a contribution. By the way, this was accepted in GRL today, this morning. So.
Great. Thank you very much, Chris. So I think we're going to move on. So again, more questions for Chris in the Slack, please. And yes, apparently I'm working off an old version of the agenda. So we have up next Faye. If Faye would like to share her screen. Thank you.
Can you see my screen?
Oh, his screen, sorry.
Okay. Hello, everyone. I'm going to introduce using inside time series to detect and model shallow continental earthquakes. Due to some fundamental limitation of INSA operation, such as deceleration and atmospheric noise, only certain earthquake can be seen on single interferogram. Here, we apply INSA time series over Iraq border area as the study case, processing 5 years known data and combine two descending track and ascending track and descending tracks. Here we can see that a large 7.3 earthquake happened in 2017 and later caused many aftershocks. We take 3 aftershocks. The magnitude of these are 6.3, 6.0, and 5.6. We find that INSA time series can help improve the detectability of earthquakes. The first figure A and figure B shows the earthquake detected by single interferogram and also seen on the INSA time series. The two dash green line shows the large 7.3 earthquake and the 6.0 earthquakes. The second example shows a 5.6 earthquake is not detected by the single interferogram. but the offset can still observe in the time series. Here, also with only seven observations, we see the offset both the 6.3 earthquake and the 5.3 6 earthquakes. And use this advantage, we model the seismic circle surface displacement by this equation, where here we only consider the large seismic deformation from the 7.3 and model all the other small earthquakes simultaneously due to their close in space and time. The reconstructed interferogram shown here, we can see that the reconstructed interferogram not only improve the detectability, but also make the interferogram much more cleaner and more close to the modeling result. The last, we model the earthquake by the GBS inversion software, and we currently only do the 6.3, 5.6 earthquake. And we can see that the reconstructed interferogram achieved more close to the seismology observation, but also have the narrow confidence interval. And the rest of other two earthquakes, due to the lack of coverage, we're reprocessing the data right now. So we may hope to achieve the similar results from this earthquake. So thank you for listening.
Great, thank you very much, Faye. That's really interesting work. Are any questions for Faye? I've got one to start then, which is, currently it looks like you're doing everything on a pixel by pixel basis. Is there anything to gain by imposing any kind of spatial constraint on relationship between nearby pixels, do you think?
Yeah, I'm thinking of it, but currently the pixel by pixel method is quite useful. So I'm thinking about using the spatial filtering to do so instead of by the constraint, I think, yeah.
Okay. Great, thank you. Any other questions for Faye? Okay, so then if you have further ones, please put them in the Slack. We'll move on. So we've got, as our last poster then in this session is Wendy Tsai. So if Wendy, share, thank you.
Can you see my screen now?
Yeah, we can see that. So
Okay.
I've got 2 minutes.
Hi, I'm Wendy, and my study focuses on the paleo earthquake happened along the Zhangjiaran Fault in the northern Tian Shan, and I also use INSAR to study its current deformation. In order to know about the rupture processes of the intraplate fault, we'd like to study the surface ruptures along one of the major intraplate structures. We want to know how big and what happens during the last event here, and what's the earthquake occurrences along the Zhangjiaran Fault. We first used lots of imageries to identify geomorphic features for mapping out the fault and for measuring the surface displacements that could be found. Based on the mapping results, we separated the Zhangjiaran Fault into 7 sections, but we found the fresh surface ruptures only appear between section 2 to 5, which could be a constraint for the rupture length. Also, the southern sections are dominated by pure strike slip motion, whereas the northern parts have both reverse and lateral components. We further found that the average slip in the southern part is 7 to 9 meters. As for the northern parts, the average slip is harder to tell, but we found the ratio of lateral to vertical slip, which could help us do this estimation. By assuming the sensitive vector and the usage of this ratio, we calculate the average slip in the north to be 8 to 10 meters. Although we couldn't be sure about the exact rupture length, we suggest all possible rupture scenarios and found the magnitude for the last event here to be 7.7 to 8.3. As for the INSAR processing, we faced the unwrapping challenges because of topography and also the regions around the fans and the fields. So we used some approaches to deal with the severe topographic and moisture delay with the empirical direction and also a PCM model. After removing the high amplitude seasonal signal and the high misclosure area, we can see there is still a line of sight velocity change across the fault, which showing the current deformation of it. So here are some conclusions we got so far, but there are still problems to be solved and more INSAR processing are needed for a more valid results. Sorry for the abundant information, and there are more detailed slides and posters on Slack. And thank you very much.
Great, thank you very much, Wendy. Okay, so are there any questions now for Wendy? We have a little bit of time before this session is due to go over to the full poster session on Slack. So Luke Webmore asks, how did you decide on your segments?
So basically, there are the lateral sleep distribution somehow concentrated only in certain sections. So we based on the strike and the type of the sleep to try to differentiate different sections, and also based on the geomorphology, because the section seems to be corresponding to the topography of the Hamilton belt. So that's how I separated the sections.
Great, thank you. So unless there are any more burning questions for Wendy, I think we should thank all of our poster speakers once again. That was very good, and everyone kept on time very nicely. So if we could all thank our speakers. And now we have essentially half an hour, so until 1:45, to move over to Slack. Please post your questions there. Hopefully we'll get a really good discussion up and going. And then we'll be back here on the main Zoom channel at 1:45 for our final keynote speaker, that's Simon Kahn. Thank you, everybody.
Thanks, Rich. Sorry, I forgot to mute myself after, I don't know if my typing came through in the sound.
No, I think you were fine. I didn't hear any typing.
All right, cool. Thanks, man.
Cool.
Good to see you.
Posters.
Yeah.
If people